Hello students. So this is about the chemical properties of haloalkanes and the haloarenes. Okay, and we discussed under that the nucleophilic substitution reaction, and SN1 reaction is completed. If you have not seen, just check my previous video regarding the important points and the order of reactivity, the stability, the factors favoring and all. So as I told, the SN1 as well as this SN2 reactions are very important for your competitive exam, at the same time for the theory part. Okay, so let us discuss regarding the SN2 reaction with mechanism. Okay, so as I told, S is nothing but a substitution, N is nothing but a nucleophilic, whereas 2 is nothing but bimolecular. So bimolecular nucleophilic substitution reaction. Okay, so the example that I have taken here is alkaline hydrolysis of a methyl chloride gives methyl alcohol. So this is an example for the SN2 reaction. Okay, alkaline hydrolysis of methyl chloride gives methyl alcohol. Simple. So take a methyl chloride. Okay, when this methyl chloride is treated with a sodium hydroxide, so chloride is a good leaving group, or I could say it's a weak nucleophile. Okay, it is being replaced by the OH minus, which is a strong nucleophile. So OH will be substituted in the place of chloride, and chloride comes out and reacts with the sodium to give sodium chloride, and the required product will be formed. So alkaline, since we are using a base here, hydrolysis of methyl chloride gives methyl alcohol. So this is the reaction. Now how exactly the reaction will going to happen? Okay, that is what we are going to call it as a mechanism. See here what happens. So this is methyl. I have written an open structure where the carbon is surrounded by the 3 hydrogen and one chlorine group over here. Okay, so now the point you have to concentrate here is that the hydrogen atom having the 1 electron each are very small in size, I could say. Okay, when compared to the chlorine atom. Okay, the atomic number of a chlorine is 17. Obviously it is bigger size than that of a hydrogen. So front side of a carbon is occupied by the bulky group over here. Okay, this is the bulky group. Okay, so 3 hydrogen atoms are also surrounded, which are not a bulky group. So here what happens, the nucleophile, if it need to attack, if for example I'll take a OH minus, which is a nucleophile. So if the nucleophile want to attack from the front side, already this front side of a carbon is surrounded or occupied by the bulky group like this. Okay, so there is no space for the hydroxyl group to come and form a bond with the carbon. So for that reason, here what happens, the back side of a carbon, okay, the back side of a carbon, we are going to call it as a rear side of a carbon, is totally free. Okay, so you could see this side is free, so that the hydroxyl or hydroxide group, which is a strong nucleophile, will attack the carbon from the rear side. So here what happens, the mechanism involves a single step here. What happens, the nucleophile try to attack the carbon from the back side. At the same time here what happens, carbon, hydrogen we have, okay, hydrogen and hydrogen. So here carbon chloride bond becomes weak, tries to break. Okay, at the same time carbon hydroxyl group bonds start forming. The making of the COH bond takes place, at the same time the breaking of the CCl bond takes place. Okay, so this state is called transition state or intermediate step, we're going to say. So usually what happens, the transition state is an unstable state. Okay, usually the transition state is an unstable state. Why unstable? You could see here carbon is bearing 1, 2, 3, 4, 5 bond over here, but we know the valency of a carbon is only 4. Here what happens, the CCl bond will start breaking and the COH bond start forming. Okay, so this is transition state, which is an unstable state. Very important. This is an unstable state. Okay, so the attack of this nucleophile and the formation of a transition state is the slowest step of the reaction. Means this step will take place very easily or very slowly. Why? Because obviously the bond need to form here, at the same time the bond need to break here. It takes time, so it's the slowest step. So I could say it as a rate determining step. If I want to find out the velocity of the rate, at what speed the reaction is happening, I need to consider this transition state. Okay, next what happens here, CCl bond breaks, okay, and the COH bond finally will get, so here hydrogen, hydrogen and hydrogen, and OH will be formed. Okay, so this is methyl alcohol and chloride comes out. Okay, so this is how the reaction will going to happen. So you could see, just observe, initially the methyl chloride was like this, okay, and the OH was attacking from the back side. When it attacks, what happens? The structure will become like this. Totally the configuration is inversed or changed, I could say. It is simply like a, I could say like a umbrella. See, initially the umbrella was like this. Okay, initially the umbrella was like this. Okay, or here you could say, so how it was, the Cl group was here. Okay, when the OH group will come and attach here, the umbrella will become in this way. This remains as it is, it spreads like this. Okay, so just reversed. So this is what we're going to call it as a SN2 mechanism. So the reason of calling here as a 2, why? Just observe. In the slowest step of the reaction, as I told, it's a rate determining. So it includes both the nucleophile, right? At the same time, the alkyl halide. Okay, means the rate of a reaction is directly proportional to the concentration of alkyl halide that we have taken. At the same time, the concentration of a nucleophile that we have taken. Okay, so if I increase the concentration of alkyl halide, the rate or speed of a reaction also increases. If I increase the concentration of a nucleophile, it also increases. So it's a second order kinetics, means the rate of a reaction depends on the concentration of a both reactant. Okay, that's why we're going to call it as a SN2 reaction, bimolecular nucleophilic substitution reaction. This is the main point. Next one is, so we got to know slowest step and the rate of a reaction. Okay, next comes the order of reactivity. What do you mean by order of reactivity? See, we saw in SN1 reaction, in SN1 reaction, tertiary carbocation was more stable or more reactive than secondary than primary. Okay, but in case of SN2, primary alkyl halide readily undergo SN2 followed secondary followed by tertiary. Why it is so? It is because, see, instead of taking this methyl, which is a primary halide, if I take the tertiary chloride over here, what happens? All the three alkyl group are bulky in nature. At the same time, this chloride is also bulky in nature. If OH group, which is also bulky in nature, don't have any space to come and attack, or right? So for that reason, if the lesser atoms are surrounding, less size or low bulky group are surrounding, then the reaction will happen very fast and the reactivity will be more. So that's why primary is more reactive followed by secondary followed by tertiary. Next, if the reaction need to be carried out in a medium. So here the preferred medium is polar aprotic solvent. Polar aprotic solvents. Reason, acetone. For example, if I take a acetone, okay, dimethyl like formaldehyde like this, a different, okay, polar aprotic solvent will be taken. Why? Because if the polar protein. For example, if I use a water over here instead of this acetone or DMF, this water may combine. Since it is a polar, we are going to get H plus and the OH minus. Since it H plus formed may combine with this OH minus, which is a nucleophile, okay, may stop the reaction. So for that reason, we will going to use the polar aprotic solvent, which will not going to give any H plus or proton. Okay. So acetone and the DMF or such are example, or we can take as a solvent in case of a SN2 mechanism. Okay. Similarly, here you could see there is a change in the configuration. Okay. So this SN2 mechanism is specially involves inversion of configuration, which is well known as a Walden inversion. Very important, which is well known as a Walden inversion, where the Walden inversion could be seen in case of a SN2 mechanism. So this is about a simple explanation regarding the SN1 and SN2 mechanism. So we are going to discuss some CET and the NEET questions based on this nucleophilic substitution reaction. Then it will be very helpful for you even for the competitive exam. Thank you.